Hello everyone. It's truly an honor to join JACC ACR Pulse. I'm Sunghoon Joo, CTO at Buno, and I'm excited to share how AI models are developed and validated for clinical use. This landmark study, published in Nature Medicine in 2019, showed that deep neural network can detect arrhythmia from single-lead ECGs with cardiologist-level accuracy. The algorithm achieved very high accuracy, comparable to or even exceeding individual cardiologists across multiple rhythm categories. This 2019 Nature Medicine study, at the time, it was considered impossible to identify low ejection fraction using only ECG. Showing that AI made this possible highlight the clinical impact of using ECG as a simple and widely available screening tool for heart failure. This study shows something really interesting. AI was able to pick up the risk of AFib even when the ECG looked completely normal. In other words, the model could separate AFib patients from healthy people, even if there was no AFib happening at the time of the test. That's very powerful clinically. It tells us that a standard ECG, which look fine to a doctor's eye, may still have hidden patterns pointing to future AFib. And that opens the door to finding high-risk patients earlier and starting preventive care before complications occur. ECG interpretation by physicians has been limited to detecting arrhythmia, electrolyte imbalancing, or acute myocardial infarction based on visible patterns. With deep learning, however, we can not only improve diagnostic accuracy and speed, but also expand the scope of disease detection from ECGs. Nowadays, studies have demonstrated that AI can predict conditions and diagnose new diseases such as cardiac amyloidosis, hypertrophic cardiomyopathy, diabetes, chronic kidney disease, and even mortality risk. In this way, ECG AI is moving beyond simple rhythm interpretation to become a powerful, non-invasive tool for systemic disease detection and patient risk stratification. Why ECG AI can do things once through impossible? We need to look at the role of deep learning. This slide shows the key difference between traditional machine learning and deep learning. In traditional machine learning, we start with low input data, but we need a lot of manual feature engineering. Human design feature, and then these features are used to train a traditional machine learning model to generate the data output. For example, in ECG analysis extract, features such as PR intervals, QRS duration, QT interval, heart rate, and the degree of ST segment, and then use those features to train the model. In deep learning, however, the process is more direct. The model takes a low input and automatically learns useful representation through deep neural networks. This allows the model to discover patterns directly from the data, but these approaches require a much larger amount of data. There are three main reasons why deep learning has advanced so quickly. First, we now have powerful algorithms. With deep learning framework like PyTorch, platform like Hugging Face and GitHub, and the fast sharing research through archive, AI models are being developed and improved faster than ever. Second, we have access to massive amounts of data. Landmark dataset like ImageNet or CLIP provide the foundation for training large-scale AI models. Finally, we have the computing power needed to make all this possible. Specialized hardware like NVIDIA GPUs and cloud-based platforms such as AWS allow researchers to train and deploy AI models at a huge scale. Together, these three factors, algorithm, data, and computing power have created the perfect environment for the rapid growth of AI today. From now on, I will explain how a deep learning model learns using a simple digit recognition example. Training the model to recognize 3 as 3. A deep learning model is essentially a type of function that takes a digitalized input and produces an output. When the model is randomly initialized, it generates a strange input. Each layer in deep learning model is built from matrix multiplication, addition, and activation functions. In simple terms, training a model means finding the best weight and bias through optimization. It's important to calculate the error between the model's output and correct answer. The model weights and bias must then be updated in the direction that leads. Equally important is ensuring that the model learns from many different types of the data as possible. As an example, let's look at ECG data. We first correct digitalized ECG signals where a 10-second 12-lead ECG sampled at 500 Hz procedures about 60,000 data points. These signals are then paired with clinical labels, such as whether the patient has heart failure or not. The deep learning model is trained on these labeled ECG, learning to distinguish between heart failure or not heart failure case. In this way, the model can extract meaningful patterns from raw ECG signals that may not be visible to the human eye. In the label, we first needed pair the data from the same patient. For each patient, we collect both ECGs and echocardiogram, and then label the ECG according to the left ventricular ejection fraction measured on echo. We align the data within a 14-day window to ensure accurate labeling. This procedure is what we call data labeling. Next, the low 12-lead ECG signals were preprocessed by filtering and normalization. These signals represented as lead by sample matrices were then used as an input to the network. In this way, we built a supervised learning framework where ECGs are labeled by echocardiography, allowing the model to learn meaningful patterns that corresponded to low ejection fraction. In learning, every training sample needed a label. To get good performance, we need a lot of high-quality label data. Our group used self-supervised learning for ECG AI, so the model can learn features from many unlabeled data. The first step is to train the deep learning model to recover masked ECG by itself so that it learns the features of ECG signals. In this step, we don't need labels that show which disease the ECG belongs to. More detail, in this step, the masked ECG is used as input data, and the original ECG served as a ground truth. The second step is supervised fine-tuning. In this step, we use labeled ECG, for example AMI or not AMI. We put a classification head on top of the pre-trained model and adjust it with these labels. This way, the model can do the actual diagnostic task more accurately, even with fewer labeled data. Next, let me explain data split for deep learning. We usually divide it into 3 parts: train, validation, and test. The training data is what we use to actually teach the model. We give the model ECGs and it learns to match them with the correct label. The validation set is used while training. but not for teaching. It's more like a checkpoint. We used it to tune hyperparameters and decide when we stop training. And finally, the test set. This is completely separate set of data that the model has never seen before. We only used it at the very end to check how well the model really works. The reason we split the data set like this to prevent overfitting. If we only relied on training data, the model might just memorize and fail on new data. By using validation and test set, we can check if the model is really learning general pattern, not just memorizing. In deep learning, we have a lot of hyperparameters to think about. These are the settings that control how the model learns, and depending on how we set them, the result can look very different. Examples include batch size, number of epochs, the network structure, dropout rate, weight initialization, learning rate, optimizer, and even the loss function. I won't go into each deep. The main point is there are many hyperparameters, and choosing them well is really important for good performance of model. Tuning hyperparameters can be tricky, but platforms like weight and biases or open source tools like MLflow make it much easier. They run lots of experiments and quickly point us to the best setting, so we don't have to guess by hand. This figure shows there are many experiments about the hyperparameters. We can see the performance of model. The one of most important hyperparameter is the model architecture. In the early days of ECG AI research, people often use something called the convolutional neural network, CNN. So what is CNN? It's a type of neural networks that really good at pattern finding, especially in image or signal. This demo page is designed to make the working principles of CNN really easy to understand. You can actually see how the filter look like the data and what features they capture through the interactive UI. If you're interested, I encourage you to check it out later. It's a great way to get an intuitive feel for how CNN works. Another important architecture is the transformer. It completely changed the field of natural language processing, and soon after, people realized it also worked really well for imaging. That's what we call the vision transformer or VIT. Here, images are split into the small patches, turned into embedding, and then feed into the transformer encoder, just like words in a sentence. Transformers are now being used in ECG AI as well. Here's an example from our own work. We proposed a method where ECG signals are split into patches, encoded, and then reconstructed using a shared decoder. We actually presented this research at iClear 2024, which is one of the top AI conferences. This was a key step in showing how vision transformer ideas can be effectively applied to ECG signals. Model evaluation metrics show how well a model works. ROC curve shows the trade-off between sensitivity and specificity across different cutoff values. AUROC represented the area under the ROC curve. Values closer to 1 indicated better classification performance. This usefulness of AUROC particularly useful for comparing models on dataset with severe class imbalance like healthcare data. Confusion metrics show true positive, true negative, false positive, false negative, giving detailed insight into model errors and supporting metrics like sensitivity and specificity. and F1 score. In our recent publication, we evaluated model performance using various metrics, conducting not only internal but also external validation. External validation is becoming increasingly important to demonstrate that AI models can generalize to new cohorts. In 2019, studies using single-center data and simple dataset spring for evaluation could still be published in high-impact journal. But in many publications, medical AI models show decreased performance during external validation. Even commercially available AI tools show widely varying performance, making external validation essential. Recent publications go beyond single-center testing. They run multinational external validation to check generalizability across different hospitals and populations. And to demonstrate reproducibility, they also report performance on open-source ECG dataset. To close, there are 3 key takeaways. Thank you for listening.